This Aspen tutorial is about fluid movers, so pumps, compressors, and we're going to throw in some heat exchangers as well. So the example, alternatives for preparing a feed. So a process under design requires that 100 pound-moles per hour of toluene at 70 degrees Fahrenheit, 20 psi absolute, be brought to 450 degrees Fahrenheit and 75 psi absolute. So developing 3 flow sheets. So in class, we went through the physics that are actually occurring with toluene. So here we have a liquid, here we have a vapor, and our normal boiling point is around 230 Fahrenheit. Process 1 heats up the toluene, then compresses the gas to produce our product specification. Process 2 pumps that liquid, then vaporizes it in a heat exchanger to produce our desired specification. And process 3 is a liquid pump going into a heater to heat up the liquid, then to vaporize the liquid isothermally, and then continue to heat up that vapor to our product specification. So in Aspen, we are going to see which one of these is best from an energy standpoint as well as an economic standpoint. So open a blank simulation. Now our only component is toluene. So toluene is simply just called toluene in Aspen. We can hit our next button. Now because toluene is relatively non-polar and it is our real constituent or component, I'm going to use ping Robinson. Now we hit the next button, we can go to the simulation environment, or we could simply just click simulation down here. Now under manipulators, there is a block called duplicator. This will allow us to run all 3 of those processes at the same time, so we don't have to have 3 separate sheets. So I'm going to put all the blocks on first, and then all of the streams. So if we look at our first process, we have heat exchanger and a compressor. Second process, pump and a heat exchanger. And then process 3, a pump and 3 exchangers, or 3 heaters. So coming back, under pressure changers, we have pumps and compressors. So we have a pump in process 2 and 3, and a compressor in process 1. And under exchangers, for now, we simply just want a heater and not a heat exchanger. And here's the reason why. So if we put a heater and a heat exchanger on, and we click our material, this tells us that for a heater, we simply need our fluid in and our fluid out. If it's a heat exchanger, we need our fluid in, fluid out, and then our coolant or our heating medium on the opposite side. So we need 4 streams. We simply want to look at the energy change, which is why we only have a heater. So take the heat exchanger. Let's move this heater up here. So now we have all of our units, and now we can add our streams. So we have our incoming to each process. Now I'm going to rename some of the streams and some of the units so that we can better find them in our hierarchy at the left-hand side. So process 1 out. So I'm just double clicking on these tags So heat exchanger 1 for process 1, heat exchanger 2 for process 2, and since we have 3 of them in line, heat exchanger 3-1, 3-2, and 3-3. Clean it up just a little bit. Now, for the utilities, we can go a step further right now and add in work as well as heat streams. So work streams, you can see that the pumps and the compressors will require work in the form of electricity. So if we put it as a stream coming out, that will tell us the demand that is required for those units. So compressor work and pump 2 and pump 3 work. Similarly, if we select heat, we can see the heat required by each heat exchanger. I'm going to rename these. So now we can add in all of our streams. So again, our specification is that we have 100 pound-moles per hour, 70 F, 20 psia. I'm going to select English, so everything is already in the proper units. So once we have our in stream, we can then select or go to all of our unit operations and specify everything we need to there. So first is our compressor. So we can select compressor or turbine, and we just want to pick the easy isentropic, but our discharge pressure is our actual specification of 75 psia. I'm then going to go to pump 2. So we have a pump, and now our discharge pressure or pressure increase, we can select any of these. However, we want to select discharge pressure for both pumps, but we have to work backwards in order to do that. So for C1, or for 1 out, 2 out, and 3 out, all the specifications are the same, of 450 Fahrenheit and 75 psi, which means we have to work backwards. So for pump 2, if our outlet is 75 psi, then if we have a 5 psi drop through our heat exchanger, which is fairly customary using heuristics, we can then say that our discharge pressure is 80 psi for pump 2. Similarly, for pump 3, if we work backwards, so if this is vaporizing, or sorry, heat exchanger 2 is vaporizing, and we don't have any change in pressure through there, for a boiling system, there will be a pressure drop. However, it's negligible, or we're going to neglect it for now, which means that we have our 5 psi drop roughly through heat exchanger 3, and we have a 5 psi drop through heat exchanger number 1. So 75 plus 5 is 80, so streams 10 and 11 here have pressures of 80 if we neglect pressure drop through heat exchanger 2. Heat exchanger 1 has a 5 psi drop, which means that the pump discharge pressure will be 85 psi. And now we can look at our heat exchangers. So heat exchanger 1, we can specify any of these factors. We're going to maintain or keep temperature and pressure. So pressure coming out of the heat exchanger will be 15 psi. Again, this is because if we look at our flow sheet, we have 20 psi coming in. We're going to have 5 psi drop according to heuristics or rules of thumb, and then that means that our stream 5 pressure is 15 psi. Now, as far as the temperature goes, we're going to have to guess a little bit. Due to compression, we will heat up. So our target on the back end is 450 degrees Fahrenheit. If we just pick something above boiling, so above 230, so we'll go halfway between, say about 350 or so. Heat exchanger 2 is this one here. So again, we are heating up a liquid, vaporizing that liquid, and then heating the vapor to 450. So here our valid phases, again, are vapor and liquid, as is our valid phases for heat exchanger 1. So here we can select 450 and 75 psi because those are the exit concentrate or exit temperature and pressure of our heat exchanger due to our specification. Heat exchanger 3-1. Now this is only heating up the liquid, so we can pick liquid only. We can specify that we have our 80 psi because of the 5 psi drop through the exchanger, and taking somewhat of a guess or initialization temperature, say 350, similar to heat exchanger number 1. We just want to get it to solve, and then we can tweak it from there. So again, heat exchanger 2, we can also say that our temperature is approximately 350. So we don't have a temperature increase, we are simply just changing or continuing to boil the toluene. Then heat exchanger 3, we could pick vapor only here because we are only continuing to heat the vapor produced. And here our specification is 450 and 75 psi. So we have all check marks, and now we can run our setup. So our setup or our results are available. So we can click on our streams and see what has happened for our materials. So coming out, so 1 out, 2 out, and 3 out, you can see that we do in fact get 450, or they're close enough, 450 Fahrenheit, 75 PSIA for all 3 cases. And if we care about all the other flows and everything, we can take a look down here. But again, we're only concerned with our temperature and pressure out. Here we can see the heat because of the Q streams that we put in the flow sheet. So here we have HE1Q, HE2Q, and then the 3 for the 3 heat exchangers. So here we can see roughly 2.5 million BTUs per hour is required for the first case. In the second case, for the second process, about 2.8 million BTUs an hour. And then for these others, we can see that total is a little over 3 million BTUs an hour. We can also look at our work streams. We can see that the compressor would be about 140 horsepower. Each pump is going to be about 2.5 horsepower. And now we have completed the specifications, or we've determined that process 1, 2, and 3 would require the appropriate amount of heat and energy that we see from lecture. So we got 140 horsepower. They calculated 135. Very similar. Again, the heat exchanger duties, we had 2.8 million BTUs an hour, as well as 2.5 for process 1. And then we can include the economics as well, but that will be in another video.